Right. Cool.
Right. So, on web observations of an aurora boundary.
Yeah. So, hi, I'm Eleanor. I am a first-year PhD student from the University of Sheffield, and I'm going to be talking a bit on JWST observations of aurora on a warm brown dwarf. So, observations of brown dwarfs have revealed a subsection of these objects that display highly polarized coherent radio pulses consistent with ECMI emission. Observations have also shown these objects display optical and infrared variability with the same period as these radio pulses. It was therefore proposed that a single mechanism could be used to explain both of these features, and that is an electron beam which generates the radio emission, striking the upper atmosphere of the brown dwarf, thereby creating a surface feature responsible for the optical and infrared variability. This process is analogous to auroral processes we already see on Jupiter, albeit on much larger scales, leads to the conclusion that we're seeing brown dwarf aurorae. So the object I'm going to be talking about, well, the brown dwarf I'm going to be talking about is LSRJ 1835. It is an M8.5 dwarf, meaning it is relatively warm, so we're not really expecting to see much dust. And it's also suspected to be young with low surface gravity. So back in 2015, Hallinan et al. Observed this object at both optical and radio wavelengths. They observed harmaline emission, which you can see in plot B up there, is varying in phase with nearby continuum optical emission, suggesting that they were both co-located at the same surface feature. So when modeling the variability in plot C here, they found that the surface feature could be really well approximated using a blackbody spectrum. To explain why this blackbody approximation worked, they speculated that what we're seeing is an optically thick region, with the opacity source being H- ions, the population of H- ions being enhanced by the presence of the auroral electrons. So to build on the work done back in 2015, our aim was to test the Hallinan model for optical and infrared variability using JWST. So we managed to get over one rotation period of JWST spectroscopy using NIRIS, and we also managed to get optical coverage using GTC, Megara, and OSIRIS. Moving on to our results. The first main result we have is that there's a definite change in the H-alpha variability. So these two lower plots here are dynamic spectra. So they are basically showing the variability in intensity as a function of wavelength. And all the spectra have had the mean spectrum subtracted off. So you can see the mean spectrum in these two upper panels here, overlaid over the top of all of the spectra. Looking first at the 2016 Keck-HiRES data, you can very clearly see the H-alpha variability. But when we then compare to the 2023 Megara data, you barely see this variability at all. And this is sort of the first sign that the picture we're seeing now is quite different to the picture we were seeing back in 2016, 2015. Moving on to our JWST results, we have our mean spectrum here in the blue. We actually had a really hard time matching our mean spectrum to model atmospheres. We were finding the height of the absorption bands was quite different, and also the line strengths were quite different as well. So here we instead have a comparison to another brown dwarf, PWA 27A, and its spectrum was obtained using JWST's NeoSpec instrument by Manhavakis et al. So TWA 27A is an M9 brown dwarf, which is relatively young and also with low surface gravity. So looking at the comparison of these two spectra here, you can see that they do agree reasonably well. However, there are a couple notable differences. First of all, you can see in the zoom in of the J band here that the iron hydride lines are significantly stronger in LSRJ 1835. Furthermore, you can see that the water band shapes differ. So you can see in the yellow up here, they're slightly wider, which is strange considering they are both low surface gravity. So overall, our spectrum does agree quite well with other low surface gravity M dwarfs. However, it's definitely peculiar. Moving on to the variability, we have another dynamic spectrum up here. So again, wavelength along the x-axis, time along the y-axis, and then color-coded by flux. We start off on the red data points, and the mean spectrum has been subtracted off. So we start off at the red data points here with the flux below the mean spectrum, increase up to the blue, and then decrease down to the red again. So to replicate our data, we use principal component analysis, and we found we needed two component spectra sum together variability in order to replicate our data. And you can see from our model here that it does match the data really well, and the residuals are random as well, so did a pretty good job. So here are the two PCA components here. What these components are basically showing is the maximum variability as a function of wavelength. So component 1 here you can see is dominated by iron hydride changes. We just saw in the mean spectrum that there was unusually strong iron hydride lines, and what we think this is suggesting is that we're seeing the aurora driving the abundance of the iron hydride. Component 2 here, you can also see the iron hydride variations, but you can also see there's something else, this variability in the H and K band, which I'm going to touch on in just a second. But here we have the time varying contribution plots of the two components. You can see they're both sinusoidal-like, but you can also see they are a bit out of phase. This suggests that they're both in two different locations, and we think maybe what we're seeing are the two surface features at the two magnetic poles. So what is the variability we were seeing in the H and K bands? Our current theory is that we're seeing a gray opacity feature that's variably obscuring the H and K photosphere. So that would mean our observations would be a variable mix of two spectra. So we would have the photosphere spectrum S and the obscured photosphere spectrum alpha S, where alpha is the flux drop due to the opacity feature. So here on the left, you can see this model in action. So you have the photosphere in blue up here and the obscured photosphere in orange up here. And subtracting the obscured photosphere from the photosphere, we get our variability. And we find this matches really well in the H and K bands, leaving some credence to our theory. So what are the possible sources of this opacity feature? We initially thought maybe we're seeing electron scattering off the radiation belts. However, our calculations showed we would need an electron number density of order 10 to the 14 per centimeter cubed, which is a pretty unfeasibly large number. So instead, our current theory is that we are seeing variable obscuration due to high altitude dust. And that moves on to our main conclusion that we can make is that the behavior of LSRJ 1835 has definitely changed since 2016. We're seeing a significantly smaller variability in H alpha emission. We're also seeing this iron hydride abundance, we believe, being driven by the aurora. And we think we're seeing variable dust obscuration of the H and K photosphere. So our future work is going to be focused on understanding the origin of this gray opacity feature. Is it the dust obscuration, or do we need another explanation? And doing further time-dependent retrievals. Thank you.
Question?
Like, let's go to, in slide 8, quickly said that you thought you were seeing aurora from both poles.
Yeah.
What that would require something of a specific orientation.
Mhm.
You have evidence that A, it's a specific orientation, and B, if it is that specific orientation, wouldn't you expect them to be fully 180?
Yeah.
Now let's do that.
Yeah, we're sort of, that's an idea we have, but we're not quite sure on it, basically.
I'll just add to the inclination of that system is known pretty well,
Okay, is it, John?
pretty much.
Okay, so that part works. No, I'm not being, I would also expect then the phase difference to be a little bit larger.
Question? Can you so can you tell me more about how you would produce a gray opacity source?
Um,
How that might be possible through the auroral process?
well, we think the gray opacity source would be the
Dust.
dust obscuration, yeah.
So how's that related to the auroral?
We're not quite sure yet. Basically, is the answer.
Great, thank you.
Can you get them to, is it the way that they haven't been able to get it to the speaker, so they've been switching the local to the local speaker? I'm just putting the lavalier on the computer, and that's been working.
Okay.
Yes, use the
Yeah,
speaker.
Just putting the microphone.
Okay. So we should, but you should get them zoomed in.
Okay, so can you hear me in the room?
Yeah, you do.
Probably not.
They're sharing that screen.
So Maria, could you share your screen?
Yes, sure.
And
I know. That's what they told me to do.
So can you